Hello everyone and welcome to another video. So today I'd like to talk a little bit about probability distributions. So this is a continuation of our series on probability. So if you haven't seen our introductory video on basic probability, please take a moment to watch that one first because we're going to build off some of those ideas here. So what we're talking about in probability distributions today, in terms of an outline, we're going to start with talking a little bit about random or stochastic variables, and then we're going to talk about probability distributions. We're going to see there's two types of probability distributions that we'd like to cover, one being the cumulative distribution function and the other being a probability distribution function. And we're going to look at both of those in both the discrete case and the continuous case. Once we've got that down, which is going to be the meat of the discussion, we'll talk a little bit about the mean and the variance of these distributions and talk about how to transform these mean and variance under different operations, as well as some expectations and other higher moments. So if that sounds like fun, why don't we go ahead and just get started. So starting off with this idea of random variable. So the idea with a random variable is that if you have some experiment, the quantity that we're going to observe in that experiment is called a random variable, right? Because it could take many different values. Sometimes this is also referred to as a stochastic variable. So you might hear that that nomenclature as well. But for the most part, I think random variable is good. So let's denote a random variable with capital X, okay? So if this capital X value is able to take on only discrete values, for example, like if you roll a die, right, you can only get 1, 2, 3, 4, 5, or 6 for a normal 6-sided die, right? Those are discrete values. So if that's the case, we're going to call X as a discrete random variable, right? And similarly, if that thing can take on continuous values, for example, X is the voltage on a capacitor, which can take on, any spectrum of numbers, we're going to call that a continuous random variable, right? So with that nomenclature out of the way, what we're going to be able to do now is say, okay, we know that this variable is random, and it's possible that some values are more likely than others, right? So the way we're going to parameterize that or describe that is that distribution of X, of how those values might come out in a given trial, right, is determined by what's called the distribution function. So some texts and some references will call it a distribution function. I like to call it a cumulative distribution function, and not just actually a lot of texts call it a cumulative distribution function. This is, I feel like, a more descriptive moniker, as we'll see why, and let's refer to it as such, a cumulative distribution function, okay? So what this function does, we're going to call this cumulative distribution function capital F, right? What it does is it measures the probability that if you tell me a value, this thing will tell you the probability that the random variable does not exceed your value of interest X, okay? So we'll refer to this as the CDF, or the cumulative distribution function. And again, what it's measuring is it's telling you the probability that the random variable doesn't go above this value of interest little x, okay? So that's what the cumulative distribution function does. Let's talk a little bit about how we can build this up. So it's going to be built up from the different probabilities. So let's talk about probabilities. Remember, we talked about this earlier. We're going to say that the probability of X being exactly a value A, right? We're going to call that P of X is equal to A, right? This is how likely is it that the random variable X takes on the exact value A, right? And again, you can see in a discrete case, this makes a lot of good sense, because if you roll a die, right, there's a likelihood that a 1, a 2, whatever number comes up. Each one of those values have a probability. We're going to call it here, right? Now, we can also talk about probabilities of that random variable X falling in some interval. Let's call this interval I, right? This I could be between a lower bound of A exclusive and an upper bound of B inclusive, okay? So this makes a little bit more sense in the case of a continuous variable, where you know that it's never going to end up on an exact single value, but it could take on a value in some certain range, right? So again, let's call that probability of this interval as denoted like this, right? We're going to say that the probability that X is in this interval, this notation means that what's the probability that the random variable X falls within that range, right? So if you look at this long enough, and you start thinking about combining this with our idea of the cumulative distribution function, we can start asking ourselves things like, what's the probability that a value X of my random variable, what is the probability that it falls within this range of strictly greater than A, but less than or equal to B, right? Now, if you look at that, we say, okay, the cumulative distribution function, it told us what's the probability that x does not exceed a certain value, right? So this term right here, f of b, tells me the probability that the random variable doesn't exceed the upper bound, right, of this interval. If I subtract that with the cumulative distribution function evaluated at the lower bound, right, this term here tells me the probability that the value doesn't exceed the lower bound. So the difference is actually telling me the probability that this random variable x falls within this interval a to b. Right? So great, let's keep this in mind. This is going to be useful, and we're going to go look at examples of applying this later, but this shows how we can use the cumulative distribution function to figure out what the probability that this random variable falls within a range a to b, right? Okay, so with that general idea in mind, let's now start focusing on how can we apply this to a discrete case. What if you have a discrete random variable, okay? So let's go ahead and consider a discrete random variable that takes on discrete values. Let's call it x1, x2, all the way up to xn, right? And associated with each of these values, x1 to xn, there's an associated probability that the random variable takes that value x1, x2. Let's call those probabilities p1, p2, all the way down to pn, right? And it's maybe worth noting right here that these values, x1, x2, xn, they don't have to be integer values, right? For example, what if this random variable capital X is, let's say I went shopping and I put 3 things in my basket, right? And the random variable X is the price of an item in my basket, right? So in that case, these X's, they could be, they're definitely probably not integer values. So for example, like what if X1 was like, I grabbed like a gallon of milk, it's $5.50. I grabbed something else like a pack of, or half of a ham, $17.43. And then I grab, something expensive, like a bottle of wine, $22.33, right? So you can see that x1, it's not an integer value, right? It's something else, right? Same thing with these, right? So what we're talking about right here is this probability p1 is what is the probability that the random variable is actually equal to my first one, right? Is equal to 5.5 exactly, right? And similarly down here, right? These are actually now, you can see, even though the indices, for example, P1, P2, Pn are integers, we're really not talking about integer values, right? Right? Something like that. Okay? So just keep that in mind because that's going to come into play later when we start looking at an actual concrete example, okay? So with this in mind, what we can do now is we can ask ourselves, okay, what does a cumulative distribution function look like for a discrete random variable, right? Now, what we can also do, besides looking at the cumulative distribution function, we could look at each of these individual probabilities and we can say, hey, you know what? If I know these P1, P2, Pn, that's another way to kind of describe how often or what's the distribution of this random variable x, right? So we can say that that distribution is also determined by what's referred to as the probability function, or again, what I think you'll see more commonly, and a moniker that I like better, is the probability distribution function, or the PDF, okay? So what this probability distribution function is, it's a function that all it is when your x value of interest here is equal to the value associated with any one of these, so in this case 5.5, 17.43, 22.33, whatever, it just takes on the value of the probability that's associated with this item or this value, okay? And then it's 0 otherwise, right? So this lowercase f is called the probability distribution function. Again, to contrast that with capital F, which was a cumulative distribution function, but you can kind of see that the two are related, right? They're not independent of one another. And in fact, from this probability distribution function, we can obtain the cumulative distribution function by basically all you're doing is summing up the probabilities that are associated with values that are smaller or that don't exceed your value of interest, right? So that's what this notation here is saying. We're saying the cumulative distribution function, right, can be obtained by basically just adding up probabilities that are associated with values of x which do not exceed this value of interest, right? So it's basically just summing up probabilities that are smaller. So I think the easiest way to look at this though is an example. So give me a second to erase the board and we're going to look at 2 examples of this. All right, so let's look at this in two examples. So again, I've just rewritten our definitions of the probability distribution function here and the cumulative distribution function here up in the corner so we can refer to that during the example. So let's look at the first example. This is a pretty darn standard simple case where the discrete variable of choice here is I'd like to see what is the value that a fair six-sided die turns up, right? So you just roll a die, and I think everyone will agree the sample space here is of possibilities is just 1, 2, 3, 4, 5, 6, right? Those are the only discrete values you can get. Now, what we can do is we can assign each one of these instances of the trial, right, or a potential outcome. So the first potential outcome, x1, is just 1. The second potential outcome is just 2, x3, 4, 5, right? These are the 6 outcomes. And in this case, it just so happens that the subscript index matches with the value, right? That's a little bit, I don't want to say misleading, but you'll see in a second where this, again, it doesn't have to be the same case, right? Just like we saw earlier where you're just pulling prices out of your shopping cart, right? This first result doesn't have to be an integer, right? So again, this just happens to line up, so this is going to make our understanding for this example easy, okay? So let's look at this first potential outcome. Well, the probability associated with that the random variable is equal to this first outcome value is just what is the probability that the first outcome value is, or that the random variable takes the first outcome value of 1, right? Since this is a fair die, this is going to be 1/6. And in fact, it's going to look that way for all of them, right? Every single outcome has the same probability because this is a fair die, right? So all the probabilities are 1/6. So we can make the probability distribution function really easily because all this function is it just takes on that probability value when the value x is equal to the value associated with that first outcome. So what this looks like is we just have to ask ourselves, okay, what's the probability that the outcome is a 1? Well, that's 1/6. What's the probability that it's 2? That's also 1/6. 3, it's 1/6. Everywhere it's 1/6, but it's 0 everywhere else, right? So all this function looks like, all this PDF looks like is 0, 0, 0, 0, and then a spike at 1/6 at the first outcome value. And then another spike to 1/6 at the second outcome value, et cetera, et cetera, et cetera, et cetera, right? So that's pretty darn easy to get the probability distribution function. It's really just mapping out these probabilities on the y-axis and then putting the value associated with the outcome on the x-axis, right? Now, once we have the probability distribution function down, we can get the cumulative distribution function by really just adding up probabilities as we move along the x direction, right? Just summing them up. So what that means is, let's start here at 0, right? So you see your 0, 0, 0, 0, 0, 0, 0, 0, 0. Now we come to the value of the first outcome 1. So now, according to this, we add that probability. So we add 1/6. So this function just jumps up by 1/6. And now you keep adding, right? It's still 0, right? Because now we're adding all these 0, 0, 0, and then suddenly it's just, you jump up by 1/6 again. So you can kind of see that all this is really doing, you got to think of it as is integrating the probability distribution function to get the cumulative distribution function. And again, you can kind of see where the name comes from now, right? It's just accumulating or adding or integrating or Riemann summing, however you want to think about it. We're integrating this PDF to get the CDF, right? So what you can see here is it just jumps up by values of the probabilities every time you hit the value associated with this outcome, right? So you can see that I've denoted here in some locations here where the function takes a jump. It's potentially ambiguous where the function value is. Is it down here or is it up here? So I've indicated a black dot to denote at the jump points, it actually takes the value of the higher number, right? That's the way this works, okay? Given, again, this is where we have to be a little bit careful of this being a less than or equal to versus a strictly less than, right? So for the discrete probabilities and discrete random variables, we got to be a little bit careful about the greater than or equal versus greater than, et cetera, right? So that's what we end up with this, right? You see it just jumps up by a value of 1/6 every single time, right? So this is pretty simple. Hopefully it gets us a little bit of an idea of how this works. So let's look at a more complex situation which might highlight these differences between the indexing and the actual values. So let's look at, let's build on this example. Okay, instead of rolling 1 die, let's roll 2 die, and then the random variable in this case is the sum of those 2 die. So I'm just going to roll 2 die, and I'm going to add up their face values, and then that's the random variable. All right, so I made a little matrix here to kind of help us understand this. So let's say this is the value of the first die. here's the value of the second die. So this matrix basically gives you all possible sums that are going to come out of this, right? So you can see you have 2, 3, 4, 5, 6, 7, 8, all the way up to 12, right? So the sample space in this case is actually 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because there's absolutely no way you ever get a 1, right? So what's interesting about this, though, is now the first result here, let's call this x1, right? That's the first outcome. And then here's x2, x3, all the way up to x11, right? So I've enumerated them out here, right? So the first possible result, x1, is actually the number 2, right? It's the value 2. Similarly, the second outcome is the number 3. So we see there's only 11 possible outcomes here. So, yeah, again, I think we should just call this out because we want to make sure that we're clear here that the first outcome is actually the number 2. So the indexing, you can almost think of in your head as off by 1. Sometimes I've heard this referred to as a Star Wars error. You know why this is called a Star Wars error? When you're off by 1? You're OB1 or OB1, get it? Okay, anyway. That's the way that we're going to number them, right? Now, let's go and look at the probability of P1. So the probability P1, it's the probability that the random variable takes on the first value or first possible result, which in this case is 2, right? So P1 is actually measuring what's the probability that the random variable takes on the value of 2. Well, we can come over to this matrix and we can look at this, right? We can see there's only one possible way that happens. You have to roll a 1 and a 1. Right? And again, since both of these die are fair and they're independent events, every one of these 36 outcomes is equally likely, so there's only one possible chance of that. So the only way that you get this, you have a 1 in 36 chance of this, right? So the probability for P1 is 1 in 36. Similarly, what is the probability P2? P2 is the probability that the random variable takes on the second value, which is 3 in this case. Right? And again, you look in this case, in this matrix, there's 2 possible solutions for there. 2 ways you can do this. You can roll a 2 and a 1, or you can roll a 1 and then a 2. So that gets us basically 2 out of 36. And you can see this pattern repeats, right? So we can quickly enumerate all of the possible probabilities for any one of these 11 possible outcomes, right? So again, let's go ahead and do our probability distribution function based on this. So again, it's just 0, 0, 0, 0, 0 until you come to the value of one of these possible outcomes. So in this case, we come to 2. What is the probability that x is equal to 2? Well, we just laid that out. It is P1, or 1 out of 36. So this thing just jumps up to 1 over 36. Then it becomes 0 again, 0 again. Now, come to this one. This is 3. So the probability distribution function lowercase f measures what's the probability that the random variable will take on this value 3, right? What is the probability that x is equal to 3? Well, that's 2 out of 36. So this thing jumps up to a 2 out of 36, and et cetera, et cetera, et cetera. So what's interesting is you get this distribution here. So what's fascinating a little bit, maybe we should call this out, is that one die had a pretty much a flat uniform distribution, but now we're adding 2 of these together, and you actually get this sort of mound-shaped probability distribution function. So we'll revisit this later when we start talking about normal distributions and the central limit theorem, but I just wanted to call that out and just maybe draw that to your attention right now. So again, this is what the probability distribution function looks like, right? So now what we can do is, again, we can go ahead and, from the probability distribution function, obtain the cumulative distribution function by basically integrating or summing or cumulating the PDF. So again, all this thing looks like is we start here at 0, 0, 0, 0, then we come to the first value of x of 2, right? And we see that this jumps up by 1 over 36. So this vertical jump here is 1 out of 36. Then you keep, it's flat, 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 and then we come to here, 3. Now we see this probability we got to add on now or integrate or accumulate is 2 out of 36. So this jump becomes 2 out of 36, right? And then you keep integrating. Now it's 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. And then we end up coming to where it starts going, the drops are not as big, right? Because we're kind of coming down this side of the PDF. So again, you get this interestingly shaped CDF from integrating the PDF, right? Okay, so that's what we've got. Now, with all this in mind, maybe let's ask ourselves kind of an interesting corollary question. So with all this information, what if I want to look at what's the probability that the random variable falls in this interval, which is 3 exclusive to 8 inclusive. In other words, I want to understand what's the probability that the roll of the dice is greater than 3 but does not exceed 8, right? Or in other words, we could say, what is the probability that that you get a 4, 5, 6, 7, or 8? Right? That's what we're looking for. That's another way to ask it. What's the probability that you roll 2 dice, you add them together, you either get 4, 5, 6, 7, or 8, right? Well, according to our discussion earlier, we said we can use the cumulative distribution function to obtain this answer, right? We need to basically look at what's a cumulative distribution function at the upper limit minus the cumulative distribution of the lower limit. And again, I will just call out, make sure you keep in mind, this is a greater than, this is a whatever. This is strictly greater, this is greater or equal to, right? Okay, so to do that, let's compute these two terms first. Let's get F3 easier, capital F3, right? This is the cumulative distribution function evaluated at the value 3, right? So again, we could either just read this off the graph, or remember the way we got this was we summed up all of the probabilities of the results which were associated with values less than our value of interest, right? Less than or the 3. So in other words, we have to add up what's the probability that x is equal to 2, right? And what's the probability that x is equal to 3? And again, this is where our little off by 1 error, you guys should be very careful about how we're counting, right? This thing right here, right? Probability that x is equal to 2, that is this right here, which we happen to have called P1. Again, this was just our off by 1 indexing error or OB1 problem we have to deal with in this particular example. But long story short, it's just this value 1 out of 36, right? So this is P1 right here, which is 1 out of 36. Now let's look at this one. Probability that x is equal to 3, that is right here, right? The probability that x is equal to 3 is 2 out of 36. We happen to have called that P2. It was our second probability because it was the probability of the second output, right? Or second result, right? So it's 2 out of 36. So we end up with the overall probability here of F3 is 1/12, right? And then you do the exact same thing for the upper limit. Of course, there's going to be more terms that you're going to have to integrate, so you can get that out of as 13 out of 18. Again, you could also read this off the chart, right? Off of your CDF, right? So P3, excuse me, right here, sorry, F3, capital F3, that's this. It's this function value right here. Let me do this in another color, right? It's this guy right here, right? And again, what's interesting about this is it is right here at the jump, but that's why we have the black dots to denote what value the function takes at this jump. So we see it's up here, so that is, again, 3 out of 36 or 1/12, the same thing, right? So anyway, long story short, we get capital F3, we get capital F8. Their difference then gives us the probability that the random variable is in this range of interest of 4, 5, 6, 7, 8. We end up with an answer of 22 out of 36, okay? All right, so that's what's interesting about this. You can see that in the case of discrete random variables and discrete PDFs and discrete CDFs, we have to be a little bit careful of where the indexing is and which value we particularly take if you would like to get the right answer. So let's now compare and contrast that with what if you have a continuous random variable. All right, so now let's turn our attention to continuous random variables and continuous probability distribution functions. So again, we can talk about the cumulative distribution function just like we did earlier, right? The definition remains the same, right? It still just measures what's the probability that the continuous random variable, right, does not exceed a given value x, right? And from this, we could see that there's still the relationship now between the CDF and the PDF in the sense that you get the CDF by integrating the PDF, just like we saw earlier, except now we got to remember that x is now continuous, right? It's not a set of discrete values, right? And likewise, we can just kind of take the different, we can instead of integrate, we could differentiate. Again, we see that the relationship is that the PDF is the derivative of the CDF, right? When you take the CDF with the derivative with respect to the independent variable x, right? So this is all still the same, okay? So we could still also talk about what is the probability that this continuous random variable now falls in this range again. Again, a is, or x is strictly greater than this lower bound, but but less than or equal to the upper bound, right? And it's still the difference between the CDFs evaluated at the upper and lower bound, right? Now, what's interesting about this in the continuous case is let's substitute our definition here for this integral for these CDFs, right? So here's the CDF at the upper bound. It's just the integral of the PDF from negative infinity to the upper bound, right? Minus the CDF at the lower bound, right? Okay, now if you remember here that a and b, right, these are the limits, so right here of the interval, we know that b is strictly greater than a. So you can rewrite these two different integrals as just a single integral, right? So it's integrating from lower limit to upper limit. So what's fascinating about this is this gives us a nice intuitive feel of how we can find the probability that the continuous random variable is in this range from a to b by looking at the PDF, right? So what the picture looks like with this is, again, let's say you have a PDF, right? So, and again, maybe we should be explicit about that because I know sometimes my handwriting is tough. This is lowercase f, right? So this is the probability distribution function, right? The PDF, right? Now, if I'm interested in finding what's the probability that the random variable, or that the random variable x is between this range of a and b in this interval, what we're really talking about right here is it says all we have to do then is just integrate the PDF between those two values, right? It's this integral, right? This area under the PDF tells you the probability that the random variable is in this interval. Now, the reason why this is a little bit simpler in continuous random variables rather than discrete random variables is, again, you can ask yourself, it doesn't really matter now if you include one single point on either edge of this distribution. What I mean by this is that, okay, technically what we're talking about here is this integral under the curve is telling us the probability that you are strictly greater than a, but less than or equal to b. But again, what's the harm? If you change this to an equal sign, right? What we're really asking about is what's the probability that you're in this region, but also including this line. So you can see that in the integral, because you're adding points of zero measure, right? Or of zero width, that doesn't change it. So here, it doesn't matter if you have this, you have this, you have, some this, all of them are the same thing. So really with the continuous distribution function, we don't need to care about it as much in terms of are these lower limits included or excluded, because all you're doing is you're adding a single point of zero measure to the integral, which doesn't change the integral, right? Okay, so great. Why don't we look at an example of this in that case? Actually, before we do that, we should also mention the other thing that's important about these continuous CDFs, right, is if we remember, right, from our basic probability, we know the probability of the random variable taking a value in the sample space, the entire sample space S, that has to be 1, right, because it's got to fall somewhere in the sample space. You combine that with this discussion we just had about the integral, and you see that the property that falls out is that when you integrate the PDF from negative infinity to positive infinity, meaning the entire possible sample space, right, this has to be 1, because what this thing on the left is saying, that is the probability that you fall into some interval. The interval is the entire possible space. So that has to be 1, right, to make this true. Okay, so with that in mind, let's look at an example, okay? Let's say I've got some candidate PDF right here, right? It looks like this. It's just 0.75 times the quantity 1 minus x squared. And if x is in this range of -1 to 1, and it's 0 otherwise, right? So I just sketched it right here. So this is the candidate PDF. So my question right now is this a valid PDF? That's maybe one thing that we should look for, right? What does it mean to be a valid PDF, right? So pretty much the only thing we need to do is we need to just make sure that the probability of it occurring in the entire sample space is 1. So what we have to do is integrate this PDF from -infinity to infinity and make sure we get 1, right? So I'm just going to go ahead and say that everyone sees that I don't need to go integrate from -infinity to infinity. The only place any action is happening is between x is -1 to +1, right? So I just have to integrate this thing, the PDF, between -1 and 1. And again, if you just run over to some symbolic tool or you do this by hand, you'll see that, yay, this thing checks out. This is indeed equal to 1. So checkbox, this is basically a valid PDF, right? Okay, so now given the PDF, let's go ahead and find the CDF, right? So the way we're going to do that again is just going to use our relationship here that the CDF is obtained by just integrating the PDF from minus infinity to x, right? So again, all you got to do is just plug that in, okay? So I'm going to integrate first from negative infinity to negative 1, right? And the reason I want to do that is because I know this is going to be a big fat 0, right? Because the thing is 0 when it's not inside this interval. So therefore, this integral doesn't matter, right? This integral is basically 0, right? As we said down here. So this is 0, right? Then I'm going to integrate from negative 1 to x, right? And we remember now x goes between negative 1 to positive 1, right? So again, if you just need to plug in this, right, into my expression, and now we're just integrating this, this term, right, which is 3/4 1 minus v squared dv from negative 1 to x, right? And what you end up with is this expression right here, right? So this is what the CDF should look like between negative 1 to 1, right? And again, it's just turning the crank on this integral, right? And again, for giggles, let's go ahead and plot this thing. So the easy way to plot this is, right, when it's outside of negative 1 to 1, it's just a big fat, wait a second. No, sorry, excuse me. Hold on. That should not be 0 otherwise. This is, whoops, sorry. I got two, this is for x greater than, sorry, this should be for x greater than or equal to negative 1, right? And this is, it should be 0 for x less than 1, negative 1, right? And then it should be, oops, no, sorry. It should look like this, right? It's flat from negative 1, and then it's this function in the range. I did have this right here. This is x in the range of negative 1 to 1, excuse me. It's this kind of sigmoidal function here, but then it's 1 when you're outside the range. Or maybe I should do it like this. Positive 1, like that, right? So great. This CDF is obtained by just integrating this PDF, right? That's what you end up with, right? Okay, so now, with this CDF in place, we can start asking ourselves questions like, for example, what's the probability that a random sample is going to be between the values of negative 1/2 and positive 1/2? And again, all we do here is we come back and we use this relationship that says, all I need to do now is integrate the PDF between these values, the lower limits of negative 1/2 to upper limits of positive 1/2, and that will get me the answer of what's the probability that the random sample will land somewhere in the range of negative 1/2 to positive 1/2. So again, it's pretty much just turning the crank to do this, right? So we're going to evaluate the CDF at the upper limit of 1/2 right here, right? And then evaluate at the lower limit down here, and basically just take the difference, right? So it's just this distance effectively is the area of this integral over here. So in this case, it turns out to be 0.6875. So it's a 68.75% chance that during a experiment, one trial of this, you're going to land in this range, right? So another related question that you might have then is, what's the value x that you need to have so that 95% of your samples fall within that interval, right? So you could ask here is, what's the chance, what value x do you need to have to capture 95% of the sample? So in this case, you saw that, okay, we captured, what, 68% of the samples. How big does x have to be so that I capture 95% of them? So what we're really looking for is, if you come here to the CDF curve, we're looking for the point here where you're at 0.95, right? So we're really trying to find what is this value of x here, okay? So all you need to do is basically go ahead and plug in our expression for our CDF, right? We're asking ourselves, the interval now is, I want to capture all the samples from some x, I don't know what the x is, all the way to negative infinity, right? And I want the probability that I land in this range of from negative infinity to x to be 95%, right? So again, it's just plug and chug. We are going to make a note here that f at negative infinity, right? What's the CDF at negative infinity? That's way out here, right? That's a big fat 0, right? So this guy goes away. That's 0. So now this guy is the CDF here, right? Because I know it's going to be somewhere in this range. So this function right here of the CDF, it's this term up here. So I just plug that in here, and I need to now solve for this for the x values that make this equal to 95, right? So as you can see, this is a cubic, so we're going to come up with 3 answers. And again, if you look at these, the only one that makes sense in this case is this middle one, right? Because these are clearly outside the ranges of -1 to 1 for our case. So it looks like that at x is equal to, in this case, about 0.729. Right? That will capture 95% of all the samples in this case. So if x is equal to 0.729 and you run this experiment 100 times, you expect 95 of them to be actually lower than that value, right? Okay, great. So, okay, I hope that helps out. Let me, give me a second to erase the board and let's talk about the mean and the variance of some of these distributions. All right, so now that we've got these PDFs and CDFs down, let's talk about things like their variance and their mean. So, you remember we talked about the mean of a bunch of random samples in our previous video, but now, like we said, now that we have the PDF, we can talk about the mean of that PDF. So for a discrete case, it's just given by this, right? You sum up all of the values times their probabilities over all of the sample space. And then for a continuous distribution, the mean of that continuous PDF is basically x times the PDF, and you just integrate this quantity from -infinity to +infinity, right? These are sometimes also referred to as the expected value. It's basically the same thing, and they sort of tell you where the middle, or effectively where on average a value is going to land given this PDF, okay? And we're going to look at an example in a second. Same thing with this idea of variance and standard deviation, right? We also talked about this earlier, the standard deviation sigma, and then the variance sigma squared. Again, the variance is probably the easier one to talk about. So the variance for a discrete case is just you take the sample minus the mean, square it, and then multiply it by its probability, right? And then similarly, the variance for a continuous case looks very darn similar, except we just replace the summation with an integration, right? So let's look at an example of this. Let's look at an example of the discrete one first. So in this case, let's talk about a really simple discrete PDF. We're just flipping a coin, a two-sided coin, over and over and over, and I'm interested in the number of heads that show up, right? So the probabilities are you can either get 0, meaning you get a tails, or the probability, the other result is a 1, meaning you get a heads. And since this is a fair coin, each of these probabilities are a half, right? So I can easily calculate the mean of this distribution by using this expression over here. It's just the value times the probability plus value times probability, right? So it's 0 times a half plus 1 times a half, and you get a half, right? So again, what this means is on average, you play this game a whole ton, and you expect that the value that comes up is a half. Again, this is a little interesting because we see that 1/2 is not in the sample space, right? You don't have to have the mean be an actual value in your sample space. Again, what this is telling you is that effectively you do this over and over, you're going to land somewhere in the middle, right, of these two outcomes of 0 and 1, which again makes perfectly good sense for this this game of flipping a fair coin. We can also calculate the variance. This doesn't make quite as much intuitive sense, but we will. It will hopefully be a little more clear in a second. So let me just put this up here on the board. If you want to calculate it yourself, you should also get a quarter like I did here using the expression we had over here, right? Now, let's look at a continuous case to get a good handle on what this variance is telling us. Let's look at this continuous example. Let's say you've got some PDF that looks like this. It's just the quantity 1 over b minus a if you're in the interval of ab, and then it's 0 otherwise. This is sometimes also referred to as the uniform distribution, and the reason why is because if you plot this thing, it looks like this, right? What this basically says is between any value of a and b, right, in your interval, any value or any number is equally likely. It's uniform, right? It doesn't matter if it's a 2 or a 3 or 3.5 or a 3.8 or whatever, right? Or any interval. It's basically you get the same probability, right? This thing is flat, right? Okay, so this is what this distribution looks like. Again, I've chosen A and B to be 2 and 5 when I plotted this, just for illustrative purposes. So let's calculate the mean of this distribution, right? So the mean of this, again, is you just need to plug in our expression over there and perform the integral. So it's just x times the PDF, integrate from -infinity to infinity. So x times the PDF, right here, but since I don't need to go between minus infinity and infinity, I know the only action is between a and b, I'm going to go integrate from between a and b, right? So you turn the crank on this integral and you get this as the mean. It's a plus b over 2. So if you plot this out, you'll see what this is it's basically a over b over 2. In this case, in our case, it's what? 5 plus 3, or sorry, 5 plus 2, which is 7 divided by 2, so it's 3.5. So here's where the mean is, right? So here's mu. So it's basically, as you can see, it's sort of kind of in the middle of this uniform distribution, right? It falls perfectly in the middle because this is perfectly flat and symmetrical about mu, right? If this PDF had more weight on one side or the other, you could see how this would get shifted one way or the other, right? And again, the physical interpretation of this is if you keep running this experiment over and over and over, you're most likely going to get values near mu, right? Near this number, right? Okay, let's now calculate the variance. The variance is where this kind of gets interesting and helps us understand what it means. So the variance, again, we're just going to go ahead and use our expression over here. It's just integrate x minus mu squared times the PDF, right? So I just plug that in. We know what mu is now. We just solved for it. So it's x minus mu squared times the PDF, which is this guy. And again, I'm only going to integrate from minus a, or from a to b instead of from minus infinity to infinity. And again, you turn the crank on this and you come up with this expression. It's 1/12 a minus b squared, right? So what's interesting about this is you can see that if a and b change, I can actually keep this mu the same. For example, what if I chose another distribution that what if I chose, let's move b up by 1 unit, so maybe let's call this like b prime, and let's move a down by 1 unit, let's call this a prime, right? So now what this distribution looks like is it's something like this, right? It's got to be a little bit shorter now, right? Okay? Okay, so what's interesting is this distribution, the red distribution, if you compute this, because I moved A up by a unit and B down by a unit, by the same amount, you divide by 2, you basically end up with the exact same mu, right? So mu didn't change. The mean or the expected value of this red distribution is the same as the blue distribution. Now, physically, what's the difference between these? In the blue distribution, you know you're only going to get values between 2 and 5, right? So the most that you can get away from this mean is, you know, I don't know, what is that, 1.5 units in either direction. So there's much more certainty that in this case, with blue, you are going to get values that fall closer to the mean, right? Whereas in the red distribution, it's likely that you could get values that are farther away. So the variance is almost telling you the spread or how much variability from the mean there is in this PDF. And again, you can see that in this case. Now, this is actually measuring the spread. It's the actual distance, right? This term a minus b is giving you the distance, right? This is a minus b. Or right, a minus b squared, right? It's effectively it's that term. That's related to this term down here, right? So as the spread increases, the variance increases. So what the variance is telling us is how much of this is spread out around from the mean, right? So distributions that have more likelihood or have possibilities of numbers farther away from the mean are going to have a higher variance, right? So again, the mean or mu is giving you some idea of where you would expect most of the values to fall if you play this game over and over, you execute this experiment over and over, whereas the variance is telling you how much of a spread or variability there are in those samples, okay? Okay, let me erase the board and let's talk about mean and variance a little bit more. All right, so with that under our belts, let's talk about potentially transforming random variables and how that might affect their mean and their variance. So, for example, let's say you've got some random variable x, right? And now let's say this goes through some kind of function or some kind of process, right? Where it basically, this is effectively a linear transformation, right? This looks like y equals mx plus b, right? So if you do that with a random variable, right, what's going to happen to the mean and variance of this new signal x star, right? Well, it turns out that in that case, if you know what the mean and variance is of the original variable x, right, the new mean and variance of x star, they're going to be transformed like this. The new mean, it's going to be the old mean times a2 plus sort of the y offset. And the variance of the new variable is going to be the variance of the old variable times a2 squared. Okay, so again, what this means is, again, you've got some random variable and then you are going to transform it like this through this linear operation. So for example, I don't know, maybe this is like voltage of your battery, right? And coming out here is power outputted by the motor, right, of your car. Let's say this is an electric car, and it's really simple that the power is linearly, or more precisely, affinely related to the battery voltage through this affine transformation, right? So if I know that my battery voltage has a certain amount of, here's my mean of it, and here's the variance, how much spread or variability there is in the battery properties here, right? This is the properties of the voltage. By the time I turn that power or that voltage into some power output by the motor, the power output variability in terms of its variance and its mean here are going to be transformed like this, right? So this is what's a little bit interesting about it. What makes this interesting about this is that we can use this information to create what's sometimes referred to as a standardized or a standard random variable. Let's say, let's call it z here. And the way we do that is we take the random variable x, we subtract its mean from it, and we divide by its standard deviation here, right? Whoops, sorry, I should make sure. Yeah, right, this is all consistent, right? Again, the only thing to note here is I want to call out that you divide by its standard deviation, right? Not by its variance, okay? So if you do that, what ends up happening is that you transform this random variable x into this random variable z, and what's fascinating about this random variable z is that it's going to have a mean of 0 and a variance of exactly 1. Right? So this is going to be helpful later when we start looking at things like Gaussian distributions and normal distributions. So I just wanted to point that out, that sometimes you can use this standardized random variable for some of these applications, right? Okay, the last thing I think we want to cover is this idea of expectations and moments. So the variance and the mean are basically, they're probably the two most popular ways to parameterize or describe a PDF, right? Now, you can describe it with higher order moments as well. So for example, this is sometimes referred to as the kth moment of this random variable, right? And it looks like this, right? It's written as sort of the expectation of this sigma to the k. It's the integration of x to the k times the PDF, right? If you look at this thing long enough, you see that this is basically the mean, right? If k is equal to 1, you get the standard mean or the expected value, but you could also raise this to higher powers if you're interested in describing more information about this PDF. And the same thing is true for the variance, right? This is sometimes referred to as the kth central moment, right? But in this case, if k is equal to 2, right, we basically get the variance, right? Okay, so with that being said, I think this is probably a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. We're going to have more discussions on PDFs and probability distribution functions. In particular, we're going to look at some specific distributions like normal distributions, Gaussian distributions, hypergeometric, binomial distributions, all those kind of things within this context. So hopefully we'll catch you in one of these future discussions and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.